We're ready to start with our last contributed talk of the day. It will be presented by Avital, and she will talk about crypto-oriented neural architecture design. So Avital, thank you very much for making the time. It's a pleasure to have you, and the floor is yours.
Okay, thank you very much for having me here. So yes, my name is Avital. I am a PhD student from the Hebrew University of Jerusalem. And I will be presenting our work, Crypto-Oriented Neural Architecture Design, which was done together with Gil Segev, Shmuel Peleg, and Edith Hoshen. Okay, so deep neural networks have been a revolution for many applications that do not have sufficiently practical standard algorithmic solutions, such as medical diagnosis. But the use of neural networks also presents two conflicting privacy concerns. There is the issue of the sensitivity of the data. For example, if we think about the scenario where we have a hospital that would like to use the services of an external company's neural network in order to get diagnosis for MRI images, then how can the hospital get diagnosis for the images without actually revealing them to the model owner? There's also the issue of the sensitivity of the model. How can the model owner allow users to use the model without revealing it and maybe getting it compromised? And those two privacy concerns may limit or slow down the use of neural networks in many sensitive domains, such as healthcare, for example. So one promising approach to solve this problem is by using secure computation. We can think about this as a two-party computation problem, where we have the client with data X, the MRI images, and we also have the service provider with a neural network N. And we would like to modify the neural network N to operate on encrypted or encoded data using techniques from secure computation, which are mainly homomorphic encryption, garbled circuits, or secret sharing. The way this is done in practice is in a layer-by-layer conversion method. Neural networks are usually built as a composition of layers, so that we would like to take each layer and convert it into a privacy-preserving layer, so that given an encoding or encryption of the input, we would compute the composition of those private layers over the private input in order to obtain a private output that only the data owner, the hospital, could be able to decrypt or decode to reveal the actual result. This also holds for any intermediate layer. We can decrypt or decode the output of any layer to obtain the actual result of that computation. And neural networks are built using different types of layers, and we use different types of protocols for the conversion of each layer. So we have linear layers, such as convolutions, and fully connected, which is essentially matrix multiplication. We also have pooling layers, which take the maximum value or the average value over a small window in order to reduce the spatial dimension. And we also have nonlinear activations, such as the ReLU activation, which takes the maximum value between 0 and the input. We have tangent hyperbolic, we have sigmoid, and many others. But the problem is that in general, secure computation might be significantly slower than a regular computation, or it might require much higher networking bandwidth. And this really limits the use of privacy-preserving neural networks to only simple, shallow architectures. And it doesn't really apply to modern deep neural networks that are usually built using hundreds of layers. And there's been an extensive effort in the community to optimize the underlying cryptographic protocols that are used for the conversion of each layer. And this is invariant to the architecture. The protocols are converting each type of layer, and they do not consider the way that all of those layers are composed together into one architecture. We suggest a complementary approach to design new neural network architectures that are crypto-oriented and already have the limitations of secure computation in mind. The motivation for our work comes from the fact that in regular neural networks, linear computations such as the convolution layers and nonlinear computations such as ReLU or max pooling have pretty much the same computational cost, and because there are much more linear computations, then regular optimizations of neural network usually focus on those linear layers, and they tend to consider the nonlinear layers, the ReLU activations, to be free of cost. But as we all know, this is not the case in secure computation, where nonlinear computations are very expensive. So for example, if we consider the ReLU activation, then if we would use homomorphic encryption, then we would have to approximate the ReLU activation by a polynomial. And in order to achieve good accuracy, we would need to use high degree polynomials, which also comes at the cost of high computational complexity. We can use garbled circuits or secret sharing, which presents us with lighter weight protocols, but they also come at the cost of high communication around complexity. To further demonstrate this, we took 3 architectures that were already optimized for a regular efficiency. These are SqueezeNet, ShuffleNet, and Mobilenet. And we measured the runtime of the original architecture and the same architecture after we removed all of the ReLU activations. And we observed that in the non-secure setting, the nonlinearities consume less than 10% of the computation. While on the other hand, when computed in a secure manner, where we evaluated this using the TF encrypted library, which is based on secret sharing, then we saw that the nonlinearities consume more than 60% of the computation. So this really demonstrates that when we are planning or designing neural networks to be computed in a secure manner, we must take into consideration the nonlinear layers, and we cannot consider them to be free of cost. So our method suggests to reduce the number of nonlinear activations. In order to do so, we propose a novel activation layer, which we call partial activation layers. And in this layer, we take the input to an activation layer and we split the channels into 2 branches with different ratios. In this example, it's a 50-50 ratio, but we can select any other ratio we would want. And then we apply the nonlinearity, the ReLU activation on 1 branch only, and then we concatenate the results. By doing so, we are able to significantly reduce the number of nonlinear computations that need to be computed, while at the same time maintaining the nonlinear nature of the neural network, which is highly important because otherwise the neural network would just be composed of linear computations, which is essentially 1 matrix multiplication, and this is not as expressive as nonlinear neural networks. In addition, we also suggest to completely remove activation layers that make no significant impact over the accuracy. We can think about this as 0% partial activation layers, where we apply the activation function only on 0% of the channels. And we also suggest to choose nonlinear variants that have lower resource requirements. Many nonlinearities, such as the ReLU activation, have different variants, which were proposed in order to improve the training process or any other reasons. And we observed that some of them do not have a really big effect over the accuracy, while they are much more expensive from the already expensive nonlinearities, and we did not observe any justification for using such expensive variants. So some related work. Concurrently to us came out Delphi, which proposed a framework for the conversion of neural networks to privacy-preserving neural networks. And they suggested to replace some of the ReLU activations by polynomial approximation. And they also proposed a planner that would help them to automatically decide which activation layers should be approximated and which should remain exact. Later on came out a few works that use neural architecture search algorithms in order to design neural network architectures. They usually focus on binary or sparse neural networks and mainly move the location of ReLU activations. So some experiments to demonstrate the effectiveness of our approach. We evaluated different ratios in the partial activation layer. We evaluated this on the 3 architectures that I've mentioned before, SqueezeNet, ShuffleNet, and Mobilenet, and on 2 data sets, CIFAR10 and CIFAR100. And we saw that in all of those benchmarks, 50% provides a good trade-off between efficiency and accuracy. We also wanted to make sure that the neural network doesn't just ignore the linear branch in the partial activation layer. So we compare the results of the partial activation layer with scaling down the neural network by the same ratio, which simply means dropping the linear branch in the partial activation layer. And in all of our experiments, it is clear that the scaling down is inferior to partial activation layers, which really proves that the neural network learns during training how to use both the linear branch and the nonlinear branch. We also experimented with removing complete activation layers. As we evaluated our method on 3 architectures, all of them are built using a repeating building block, which is very common in modern neural network. And in all of those building blocks, we had 2 activation layers. And we found out that in each one of them, we were able to completely remove 1 activation layer with only a plausible or even no accuracy loss, while improving the communication and round complexity substantially. For example, in the Mobilenet architecture, removing 1 activation layer from each block improved the communication complexity by 48% and the round complexity by 40%. By also replacing the remaining activation layer with a 50% partial activation layer, we were able to even further improve the communication complexity to 67 in the Mobilenet architecture. We also evaluated different nonlinearities, alternative nonlinearities. So for example, the max pooling layer is very commonly used in neural networks, but when we compare this to the average pooling layer, which takes the average instead of the maximum, we did not observe a real difference or very significant difference in the accuracy, while average pooling is linear, so it is much more efficient to compute in a secure manner. So we propose to avoid using max pooling layers and going for average pooling or even strided convolutions. In addition, we also compared the ReLU activation with the ReLU 6 variant, which clips the values between 0 and 6. And as this variant is composed of 2 comparisons versus 1 comparison in the regular ReLU activation, then it costs twice as much as a regular ReLU activation, which is already quite expensive. And when we compared the accuracy, we did not observe any difference. So we proposed to avoid using expensive variants if they do not have a justification in the accuracy. I would like to now detail all of the modifications that we applied on the Mobilenet architecture. So the Mobilenet block is composed of 3 convolution layers, where the first 2 are followed by a ReLU 6 activation, and the last one is linear. So we completely removed the first activation layer, and we replaced the second one with a 50-50 activation layer, 50% partial activation, and we replaced the ReLU 6 nonlinearity with a ReLU nonlinearity. And all of those modifications enabled us to improve the communication complexity by 79% and the round complexity by 63%, with only 1% accuracy loss for CIFAR 10 and 2% accuracy loss for CIFAR 100. We also evaluated this on 2 additional datasets, MNIST and Fashion MNIST. And in this case, we used a 25% partial activation layer, which enabled us to further improve the communication complexity by to 83%. And we had no accuracy loss at all in this scenario. So we evaluated this method on the 4 datasets that I've just mentioned, CIFAR 10, CIFAR 100, MNIST and Fashion MNIST, and on 3 architectures, SqueezeNet, Shafranet, and Mobilenet. And in all of those experiments, we were able to substantially improve the communication and round complexity with having only just a minor accuracy loss. So to conclude, our goal was to improve the efficiency of privacy-preserving neural network inference. We suggested a complementary approach for the optimizations of the cryptographic protocols, and we suggest to design the neural network architectures with secure computation in mind. So we propose to reduce the number of nonlinear computations, for example, the commonly used ReLU activation. And by doing so, we are able to achieve a substantial speedup and with only a negligible accuracy loss. And in order to do so, we proposed a novel activation layer, which we called partial activation layer, that enabled us to remove most or a large amount of nonlinear computations in an activation layer, or even all of them in a single layer. And this really enables us to reduce the number of nonlinear computations while still not losing the nonlinear nature of the neural network. Thank you.
Thank you very much, Avital. It was very, very interesting. We're working on similar topics. There is one question from Victor. Maybe we still have time to answer them live. He says, could this approach be applied in the private training process as well?
Yes, I assume that by private training, you mean training on encrypted data.
Yes.
So yes, of course, it can be applied in any case. We do not even change the cryptographic conversion. This really applies to any framework that you would like to use. We simply suggest to avoid using the expensive parts, reducing number of nonlinearities, changing the amount, not applying activation on all channels. But this really applies to any architecture you would like and any conversion framework you would like. And of course, you can also apply it during the training process.
Okay, there is another question. Daniel is asking, have you tried other models too, not only neural networks? Thank you.
We did not try older models. We focused on neural networks, but we really suggest guidelines or methods for how to build models. So I assume that the same would apply to any other model that is composed of both linear and nonlinear computations. But we really focused on neural networks.
Thank you. I have also another question of my own. So maybe it's related not to what you have shown, but potentially about further work out of here. So I'm interested to know how this would scale if then you work with larger neural networks, if the accuracy would still be maintained, and also if you're considering other types of networks that had different activation functions as well.
Yeah, so we did not try other models or different activation layers, but I do believe that it would still work because we all know that neural networks tend to be way too large than what we actually need. So some activation layers can be removed. And what we found interesting in the partial activation layers is that the network did not ignore the linear layers. It still used them, but in a different way. So I do believe it would work on any activation layer and on also larger models. Perhaps the exact ratio would change, or different layers should use different ratios. But I believe that this approach would still apply to larger models as well.
Okay, thank you.